I now call to order the Society's 2512th meeting in what is now the 153rd year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein. I'm the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Now, welcome to our members, guests, and friends to tonight's PSW meeting and the lecture by David Bennett. Before we begin, I'd like to thank our sponsors. First, PSW is grateful to full-year series sponsors, PSW member Mike Helton and Mike Helton Associates, LLC. Thank you, Mike. And to the series sponsor of the spring lecture series, PSW member Joe Schulman. And finally, to the sponsor of tonight's lecture, PSW member Will Blair. Thank you, Will. We thank them all for their generous support. The Society needs your financial support to meet its expenses. And believe it or not, they're pretty high. So if you have not given or you feel you can give more than you have already given, please do not hesitate to donate. You can do so through the link on the PSW webpage, www.pswscience.org. Look for the menu item to give money. I am pleased to announce that the following new members have joined the Society. Alexander Omaya, Senior Director of Clinical and Translational Research with the Association of American Medical Colleges, interested in cognition and health systems and their improvement, who learned of PSW from his father, who spoke at PSW twice, at the 1999th meeting in 1992 and at the 2063rd meeting in 1996. Austin Hart, an attorney with Simpson Thacher, interested in logic, linguistics, quantum mechanics, astrophysics, and ecology, learned of PSW from searching the internet. Ronald Alexander, Chief Financial Officer at Dovell Technologies, interested in quantum mechanics and cosmology, who learned of PSW from PSW member Joel Bowman. And tonight's speaker, David Bennett, who learned of PSW from our invitation to him to speak here tonight, and whose interest will be clear in a small part from the lecture. Please join me in welcoming them all to membership. All members are entitled to a signed copy of Volume 17 of the Bulletin of the Philosophical Society of Washington, also known as PSW Science. If you haven't received yours, please come see me after the meeting. If you're interested in membership, you can access a membership application on the PSW website by clicking on the blue Join button at the upper right-hand corner on the home page, www.pswscience.org, and you can get there conveniently if you're here in the Powell Auditorium by taking one of the cards on the table at the back and using the QR code. All who are genuinely interested in science and willing to pay $75 or $25 if you're a student are welcome to join. Recording Secretary Scott Matthews will now present the minutes of the 2511th meeting and the lecture by Joanna Drucker on the history of alphabets.
Thank you, Larry. Good evening, everyone. On March 7th, 2025, members of the Society and their guests joined the speaker for a reception and dinner at 5:45 in the members' dining room at the Cosmos Club. Thereafter, they joined other attendees in the Powell Auditorium for the lecture proceedings. In the Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the lecture portion of the 2511th meeting of the Society to order at 8:03 p.m. Eastern Time. He began by welcoming attendees, thanking sponsors for their support, and announcing new members. Scott Matthews then read the minutes of the previous meeting, which included the lecture by Robert Smith titled The James Webb Telescope: Key Moments in Its History. The minutes were approved as read. President Milstein then introduced the speaker for the evening, Joanna Drucker of the University of California, Los Angeles. Her lecture was titled Alphabet Histories, The Origins of Letters from Antiquity to the Present. The speaker began by saying that there was a single taproot for most modern alphabets, and that, quote, the original alphabet is Semitic, it is Proto-Canaanite, and it is from the ancient Near East, end quote. She said that the creation of alphabetic writing constitutes an analysis of the key sounds of a language and the construction of symbols to represent those sounds. Drucker claimed that this process, which is distinctly different from cuneiform, hieroglyphics, and Chinese characters, began around 1700 to 1800 BCE. She described how the names of the letters, the sequence of the letters, and the sounds assigned to the letters allowed modern alphabets to be traced back to the source. Drucker discussed the fact that older forms of writing, like hieroglyphics and cuneiform, had to be established before alphabetic writing could be developed. She said that alphabetic writing required a cultural context in which writing had value, and that this value was motivated by accounting and commerce. Drucker described the Wadi El Hol inscription discovered in 1993 on the banks of the Nile River, believed to be the oldest example of phonetic alphabetic writing discovered to date. She said that these inscriptions changed our understanding of the geographic range over which the early alphabets were developed. The speaker indicated that her area of interest was the historiography of the alphabet, the history of the study of the alphabet. Drucker said that she wanted to learn how knowledge about the alphabet was developed, codified, and transmitted. She showed images of a text from 1667, wherein the author drew pictures of the anatomy of the human mouth and tongue, pronouncing various sounds and claiming that the organs of speech closely resembled the letters of the Hebrew alphabet. Drucker then presented what she called, quote, knowledge technologies in the humanities. These included textual transmission, graphical copying, compendia assembling, graph and chart ordering, artifactual and historical curating, archaeological situating, epigraphic and paleographic reading, and forensic analysis. She discussed and gave examples of each of these knowledge technologies. Drucker discussed the work of Herodotus, written in 1440 BCE, claiming that this was the oldest written text describing the origins of the alphabet. She indicated that the text was transmitted without modification for more than 2,500 years. This text indicates that the letters of the Greek alphabet were actually imported by the Phoenicians, who brought their alphabet with them along various trade routes. She described how the alphabet, created further to the east, first spread to the eastern Mediterranean kingdoms, Phoenicia, Philistine, Israel, Judea, and was then transported by land and sea to Greece and North Africa. The speaker discussed the biblical accounts of the history of the alphabet, including the story of Moses and the Ten Commandments and the two pillars of Seth. The speaker then discussed, quote, exotic alphabets, which have been accurately copied and reproduced but are not known to have been used. These included celestial alphabets, incorporating constellations and astrological signs. She presented several charts and graphs produced in the 15th and 16th century showing the relationship between characters in various ancient alphabets and demonstrating the way in which specific characters were modified over time. Drucker discussed ancient coins, many of which have readable text, which serve as important artifacts in the study of alphabets due to their robust nature and longevity. She showed images of the sarcophagus of Eshemonasar II, discovered in 1855, created in the 6th century BCE, with a detailed inscription written in the Phoenician alphabet. She claimed that this discovery was of great importance because Eshemonasar II was mentioned in the Bible, as well as several other texts, such that the translation of the inscription was unambiguous. And finally, Drucker discussed forensic studies of the alphabets, including a variety of modern analytical technologies and image processing techniques that allow scholars to read and decipher text that would otherwise be unreadable. She showed images of several artifacts, including pieces of the Dead Sea Scrolls, which were rendered legible by such technologies. The speaker ended her talk by saying that knowledge should not appear to be independent of the techniques by which it is produced and transmitted. The lecture was followed by a question and answer session. A member asked if a historical Moses actually existed, would he only be able to read Egyptian hieroglyphs? Drucker responded, quote, "That's not what the Bible suggests." She said that the biblical story claims that Moses came down from the mountain with both the tablets and the ability to read them. A guest asked about the Armenian alphabet, particularly with respect to other phonetic alphabets. Drucker responded that the Armenian alphabet represented a, quote, "deliberate intervention," wherein an individual dictated specific changes to the symbols, but that Armenian was nonetheless a phonetic alphabet. A guest on the live stream asked what progress had been made in deciphering Linear A from Crete. Drucker claimed that as far as she is aware, Linear A has not been deciphered. She indicated that she found this to be surprising given the level of sophistication of current cryptography and artificial intelligence. After the question and answer period, President Milstein thanked the speaker and presented her with a PSW rosette, a signed copy of the announcement of her talk, and a signed copy of Volume 17 of the PSW Bulletin. He then announced speakers of upcoming lectures, made a number of housekeeping announcements, and invited guests to join the Society. He adjourned the 2,511th meeting of the Society at 9:52 p.m. Eastern Time. Temperature in Washington, D.C., 10 degrees Celsius. Weather, cloudy. Attendance in the Powell Auditorium, 90. Viewers on the live stream, 38. For a total of 128 viewers. Views of the video in the first 2 weeks, 533. Respectfully submitted, Scott Matthews, Recording Secretary.
Thank you, Scott, for an excellent summary of the previous lecture. I'll take a motion to accept the minutes as read. A second. All in favor? All opposed? The minutes are accepted as read and will be posted to the website in due course. We now turn to tonight's lecture by Dave Bennett. Dave is senior research scientist at the NASA Goddard Space Flight Center and at the University of Maryland. He is currently the U.S. Principal Investigator for the Microlensing Planet Observations and Astrophysics Collaboration. And he is the Science Principal Investigator for the Nancy Grace Roman Telescope Exoplanet Survey Infrastructure Team. Dave's research has been primarily on microlensing and it's used to study dark matter and exoplanets. He worked on the first gravitational microlensing survey, which made the first observation of a microlensing event. Sun Hong Rhee had the remarkable insight that a short duration feature in the observation could be due to a planet. Together, they made the first proposal for a space-based microlensing survey to realize the full potential of exoplanet microlensing, and that proposal eventually matured into the exoplanet survey programs of the Roman Space Telescope, about which you'll hear a lot tonight. Dave is an author of more than 400 scientific publications. Among other honors and awards, he's a fellow of the American Physical Society. He received the Lawrence Livermore National Laboratory Physics and Space Technology Distinguished Achievement Award, a couple of, or more than one, and he has been awarded a few NASA Group Achievement Awards. He earned a BS in mathematics at Case Western Reserve University and a PhD in physics at Stanford. All questions will be fielded after the lecture during the usual Q&A session. And with that, Dave, the stage is yours.
Okay, well, I'd like to thank the Society for inviting me. Sort of the focus of my talk is going to be this Nancy Grace Roman Space Telescope, but actually most of what I'm going to talk about is development in microlensing up until then. And much of this work is done by members of my group, shown here. So I wanted to start off with sort of a motivation. So the possibility of life on other planets and possible intelligent life on other planets has been a topic of speculation for quite a while, starting with ancient Greeks, and famous scientists like Galileo actually rejected the idea of inhabitants of other worlds. But this might have been sort of 17th century political correctness. Giordano Bruno was not inclined toward political correctness, and it did not end well for him as he was burned at the stake. Even some of our founding fathers speculated on this topic as well, in particular John Adams. And at the time, it was sort of before Darwin, pretty much everyone was a creationist. And so there's a question about, whether the universe is made only for us on the Earth, or whether there might be, inhabitants of other planets who, would maybe be our equals or something. And Adams was particularly concerned that that Thomas Jefferson might hire some professors from Europe, which did not agree with his view that all the worlds were inhabited. And so his last letter to Jefferson was recommending that no Europeans be hired to teach at the University of Virginia, which Jefferson was founding. I do not know whether Jefferson followed that advice or not. And then Thomas Paine was also a supporter of, I guess, what Adams would call the American view. And so exoplanets have been in the news since 1995, when the first exoplanet around a normal star was discovered. There's great public interest, but what's the main goal of exoplanet studies? Well, everyone knows it's extraterrestrial life, but that's a very, very hard problem. And so we have to start, we have to figure out, first of all, what we need to know if there's life on other planets. And so one thing is that we know for Earth, compared to other planets in the solar system, the Earth has temperature that's consistent with liquid water on the surface. Venus and Mars do not, although they may have had water on the surface in the past. And so if you look at different types of stars, they have brightness that's dependent on their mass. And so this habitable zone where you can have liquid water on the surface, depends on the mass of the planet. So very low mass planets have a habitable zone that's in much closer, and then very low mass stars have habitable zone that's in very close, and more massive stars have a further habitable zone that's further away from the star. But we also, and so the thing that makes these interior planets uninhabitable is this runaway greenhouse effect, is what's thought to have happened on Venus, where volcanoes produce a lot of carbon dioxide, and they have something like atmospheric pressure 70 to 80 times larger than we have on Earth, and it's mostly carbon dioxide, which makes it very hot. And then the temperature gets too cold, then the CO2 freezes out of the atmosphere, and that's thought to stymie development of life. Okay, so we're most interested in Earth-like planets, but that's, habitable zone is defined as just being sort of like the Earth, and there have been several suggestions that could change that, so a very dry planet then wouldn't have the greenhouse effect of water vapor, and so it could be in a little bit closer, but a bigger change would be sort of a super greenhouse that comes from a high density atmosphere of molecular hydrogen, which is a much stronger greenhouse effect, and that could allow planets to be habitable further out in other systems. And then there's a number of other things. There's high energy radiation that could interfere with life. Some of the planets orbiting low mass stars that would be in the habitable zone are thought to be tidally locked, which would be very different from the Earth, and maybe only parts of such a planet would be habitable. And then there's this extreme greenhouse thing, and then there's also other factors, delivery of water to Earth, and so basically, in order to really understand how a planet might become habitable, it's actually important to understand how planets form in the first place. And so one thing that astronomers are doing is sort of trying to understand the population of planets, sort of exoplanet demographics. High priorities for large NASA missions and also large ground-based telescopes are decided by these decadal surveys, which are basically a big peer review process covering sort of the entire country, but also actually getting input from scientists outside the country. And so the Nancy Grace Roman Space Telescope was the top priority of this New Worlds, New Horizons decadal survey back in 2010. And the new worlds were actually microlens worlds. And then this is confirmed by the more recent decadal survey that also supports this. And so I wanted to explain the difference between different types of astronomy. And so I would argue that theoretically, cosmology is easy. Okay, so this is a figure that comes from the COBE satellite, from the FIRAS mission, which was the FIRAS instrument, which was led by John Mather, who was also the project scientist of the mission. And so they were trying to measure the temperature of the cosmic microwave background radiation. It was predicted to follow this black body curve. And here you see that actually, in order to show the error bars on this plot, the plot is actually the data. Well, these are the data points here, but in order to show the size of the error bars, they had to magnify them by a factor of 400, because the real error bars were basically smaller than the thickness of the line, right? So that was, that actually could be confirmed with only 9 minutes of data, although this is more data than that. And another one is this discovery of the so-called Doppler peaks of the cosmic microwave background. So this is in the anisotropy of the microwave background, and the anisotropy is pretty small, about 1 part in 10 to the minus 5, and that's what makes this calculation fairly easy, as you can use perturbation theory. But the shape of this could be predicted back in 1987, and it was discovered by Boomerang, WMAP, and later Planck made these measurements, and it's unfortunately they didn't use the same scale. So this is the predictions on a log scale, and it assumes some parameters that are a little bit different here, but it predicts these peaks at exactly the same point. It just looks a little funny because it's on a log scale. But anyway, this was done from first principles, the prediction. Okay, but planet formation doesn't work like that. It's a lot more complicated. It involves a collapse. It involves a collapse that forms a star. You get this protoplanetary disk, but there's lots of physical processes that go on there. It's difficult to determine a lot of the features of these processes, and then the leading theories for planet formation are also quite complicated, and they involve a number of different processes, which you can do a specific calculation to determine accurately how some process might work, but you can't do that on the same scale as following the entire formation. And so there's a bit of guesswork involved, and so basically exoplanet theory doesn't really make any grand predictions. They have approximations that they put in the calculations, but but you need lots of different types of observations to see if their assumptions are correct. And so basically, you need basically theory follows the data. Okay, so now maybe this was not always very well understood. Back before the first exoplanets were discovered, we had a good theory that predicted a lot of well-known facts of the solar system that must certainly be true with other solar systems. So inner planets were small and rocky because they're close to the sun. Gas giants are only formed beyond the snow line, and the snow line is where basically ice is condensed. You have more solid matter available because the disk that they form out of is colder. And then also, it was thought that these gas giants would form very quickly from objects of mass of maybe Uranus or Neptune. This turned out not to be true. The Kepler satellite found lots of sub-Neptune planets, so planets similar to Neptune but smaller, in much shorter period orbits than anything in our solar system. The very first exoplanet found, or a normal star, was a mass in between Saturn and Jupiter, but in a 4-day orbit, whereas Jupiter and Saturn have orbital periods of 13 and more around 20 years. And then we also find in microlensing that the planets with masses in between Uranus and Neptune and Saturn and Jupiter are also common. So basically, the theory that was developed before the discovery of exoplanets had a lot of incorrect assumptions, and there's even one pretty prominent theorist who never believed the observations and is no longer a prominent theorist. Okay, so I'm going to mention a few exoplanet detection methods, and these are mostly going to focus on indirect methods because these are the ones that are able to tell us about the sort of population of what exoplanets are like. But there's also direct detection, and that's a lot harder. A lot of the planets that are found by direct detection already are ones that are in very young systems, and we're seeing very massive planets radiating their own light just from their generated from their gravitational collapse. Hubble and James Webb have tried to do direct detection, and they've had a little bit of success, but they're not actually missions that were designed for. They had no planet detection designed into them. The first space mission that actually is going to have direct detection designed into it is this Roman space telescope, but this is not considered a science. The coronagraph that is doing these observations is not considered a science project, but a tech demo. And that means that we don't have to prove that it'll be able to detect lots of planets before it launches. We'll be able to design something that should work, but we won't have the burden of proving it, which is very difficult to do from the ground. And so it's cost effective to do, and it will enable this Habitable Worlds Observatory. We'll try out these systems. We'll figure out maybe some problems with them and how we can fix them, and that should set the stage for a later, much larger direct detection mission. Okay, so this is showing two of the indirect methods. So reflex motion. So this is now looking at the motion of the star in response to the orbit with the planet. And so this is something that works, most easily for more massive planets. So here so here on the bottom is the astrometry method, where you can see the motion of the star in the sky in response to the planet. That's more sensitive to very long period orbits. But more discoveries have been made by radial velocities, where you look at the velocity of the star in response to the planet. And so Jupiter orbits the sun at 13 kilometers a second, and it's 1,000 times less massive. So the sun is orbiting the center of mass at 13 meters a second. And so we're able to measure the position of these spectral lines to see a Doppler shift of this motion of 13 meters a second, but they've made some measurements down to around half a meter a second. And so that you can see smaller planets, and also the velocities are faster if the orbits are very close, and so those planets are easier to detect. All right, so most of the statistics that we know about actually come from this transit method from the Kepler telescope. So this is on the right here is what happens with a Earth-sized planet moving across a star, and it decreases the brightness of the star by a 1/100th of a percent. But Kepler is able to measure that, although most of the planets found by Kepler are larger than the Earth. And the radial velocity method also helps with this and can confirm some of the planets found by Kepler. So this is now a plot showing a prediction of, showing discoveries by Kepler in red, a bunch of other discoveries by other methods, by radial velocities. Some of these are by microlensing. But then in blue is the expectation from the Roman telescope and the Roman Galactic exoplanet survey. And this is before the name got changed to Roman. It was called W first. Okay. All right. And then so this now shows the same sort of figure, but but instead of using the separation, using the location of the snow line. So that's where ices can form, and so there's more solid material to start the formation of a planet. And so basically, at present, microlensing is the only method that can find these planets beyond the snow line, down to low masses, down to around an Earth mass. All right. So gravitational microlensing is a relatively new method. I mean, people had known about gravitational lensing before, and Einstein wrote a paper in 1936 where he suggested that the method gravitational lensing would never be observed. But the thing that started off the observations was this paper by Bohdan Paczynski in 1986, saying that microlensing would be a way to check whether most of the mass of the galaxy, which is in a form of dark matter that we don't know what it is, the simplest possibility would be that it's things that are like stars but too low mass to burn, to have nuclear reactions in the core, or maybe even dead stars that had burned out. And so this spurred some, it got me excited, and a few years later, I suggested this to Charles Alcock, who then started the first microlensing observations. And then even before the first observations were taken, a student of Bohdan's, Shude Mao, who's now in China, predicted that you could find exoplanets in this way. All right, so the first microlensing event was then found 2 years after that paper about the planets, and made the cover of Nature. And so here's the first planet, and my late wife looked at this light curve, and she saw that it actually didn't quite fit the normal microlensing event due to a single mass. And there was this feature where this point is lower than expected by a single lens event. This one might be higher, and in fact, there's two models for this that explain it equally well. One has a mass ratio of 1%, and so that would be the first planet found around a normal star, but it wouldn't be one in a galaxy. Would be in a Large Magellanic Cloud, which is a galaxy you can only see from the southern hemisphere. Unfortunately, the data were not dense enough to actually distinguish this from another model that explained it as a system with basically two equal mass lens stars. But this started Sun Hong Rhee in working on this problem of understanding these multiple lens microlensing events. And this proved crucial for the development of the microlensing exoplanet detection method. Okay, so back in 94 and 95, and this was before the first exoplanet was discovered, there was this complicated review process that NASA was working on called a exploration of neighboring planet systems. And so they had 3 review panels that all came up with programs, and then they wrote reports, and then they took a third of the people from each committee and put them in one committee. And that committee recommended a ground-based microlensing program, and they actually rejected Kepler. And part of the reason that they rejected Kepler it wasn't called Kepler at the time, but part of the reason they rejected it is they thought that no planet would be easier to find in our solar system than Venus. And Venus is really hard to find because it's a little bit shorter period than Earth, but the radius is about the same. And, it's really small. The signal is really small. But just before this report was released was when this 51 Peg, a giant planet in a 4-year period orbit, was found. And actually really helped Kepler because it made it clear that there would be a lot of planets that would be easy to detect. And so there's a lot of planets that are easy to detect. You understand the method and be successful with Earths as well. But in the process of competing this, the guy who was pushing this the most was this guy here, David Tytler, who actually never worked in microlensing, but he was the most enthusiastic. He demanded that we really needed to do the calculations, including the effects of the finite size of the source star, to show that we could detect Earths this way. And so that spurred Sun Rhee and I to do these first calculations that could calculate this properly. We sent the results to this XNEPS group, and Tytler managed to find the one event that we sent him that had a systematic error in it, and use that in the report. But then this complicated system then sent this report to a blue ribbon panel that threw out the recommendation of these panels and wanted to propose a mission that would directly try to get spectra of Earth-like planets, despite the fact that we didn't know where any were. All right, so here's a diagram that sort of shows the physics of microlensing. So basically, to see the microlensing effect, you have to get lucky. And the reason is that you need to have a background star that lines up with your planetary system. Okay, so when this planetary system comes close to the line of sight, then it bends a light, and what you see is here 2 images bent by the star. But if one of those images passes close to the planet, then that can also change the microlensing event, and you can see 2 more images, or sometimes you can make the image much dimmer. And so you see these features in the light curve. And because all these stars are orbiting in our system, this alignment is a temporary thing. And so you observe the event by measuring the brightness of star constantly and seeing that they change. The difficulty is that the chance of such an alignment is only at any given time is only a few per million. And so you need to look at a field that has a lot of stars. And in fact, your detections improve sort of as the square of the star density, because you need a lot of source stars and a lot of possible lens stars. And so where we look then is out here at the orbit of the sun, we look toward the center of the galaxy, and then we're sensitive to planets near the galactic center and all the way out in the galactic disk along the line of sight. And so that's why the Roman survey we call the Roman Galactic exoplanet survey, because we're we're discovering planets throughout the galaxy, or at least the galaxy interior to us. All right, so this is, well, based on this paper by Einstein in 1936 that first introduced gravitational lensing. And so if you have like a perfect alignment between a background star and a foreground star, that's the lens, then by circular symmetry, if the alignment's perfect, you have to have circular symmetry in the image, and so you get this ring, which is referred to as Einstein ring, and this is sort of sets the scale for where the microlensing effect is important. And typically for stars toward the bulge, it's around 2 or 3 astronomical units, and so that means that our highest sensitivity when we're doing microlensing searches is, a few astronomical units, but it's only the 2-dimensional separation, not including the separation along the line of sight. And also, the magnification here in Einstein ring is quite high, much so the blue image has much larger area than the size of the source, which is red. And even if you're not quite perfect alignment, you still get these highly magnified images, one outside the Einstein ring and one inside. Okay, so this is a simulation of what the images look like in the very first planet found by microlensing, which was published. It was observed in 2003 and published in 2004. And so what you're seeing here is you're looking at the lens system, and there's a star in the center here, and then there's a planet out here, and this green thing is the Einstein ring. And so you see there's 2 images that kind of circle around the Einstein ring that is lensing by the star, and then one of them passes close to the planet, and that causes these spikes in the light curve. And these spikes are caused by new images that are created. You can see them appear near that planet. And for a point source, the amplitude of those spikes would be infinite, but they're smoothed out by the finite size of the source. But this is a characteristic feature of microlensing, and so when you see effects like this, it's pretty clear that microlensing must be causing it. All right, so this is actually a simulation of what the data for that event look like. This is basically at the resolution that the Ogle telescope got, although the planetary signal, the data actually came from the MOA telescope that proved that it was a planet, because we observed one of these caustic crossings. All right. And so that was the first planet found by microlensing. This is the third one, and the third one at the time was the lowest mass planet found by any method, at about 5.5 Earth masses. Okay, so this one involved a giant source star, and so I have a video that shows the same sort of thing as that other one, but the planet is a lot smaller, and it's actually going to be completely to scale, and so the images are a lot smaller than Einstein ring. So we have to move around to focus on the Einstein ring. So the Einstein ring is that blue ring. And then you see the 2 orange lensed images. The red circle is the position of the source. And now the planet is located right here. And you can see it's actually in the middle of that. You see the little Einstein ring there going across the face of the star. The star is distorted because of lensing by the star. So the source star is distorted by lensing by the lens star. Okay, now here's a close-up of that. And so this is one image, the second image, and then and this is the same video I showed before, but just a close-up of the planetary feature. And you can see all the features in the star sort of rotating around. That's, characteristic of the way microlensing works. Of course, we can't really see this. We're only measuring the magnification. So this now shows the same video, but now on the right, we have one with a larger mass by a factor of 3. And you see, so that makes the ring in the middle of the image larger, right? So the bending angle of a more massive planet is larger, but also the total area of the image gets larger, and it stays larger for a longer time. And that's what we see, is that the area of the image is changing, and so the brightness is changing. All right, so that's sort of what we would see if we had a super large telescope that could resolve everything. We don't expect to have a telescope like that anytime soon. So then there's a question of how low we can go, and this is this is based on the paper I worked on with my wife in 1996, and shows that basically the situation is a little different for planets inside the Einstein ring and outside the Einstein ring. But inside the Einstein ring, a giant source star makes it really difficult to find a low mass planet like the Earth. But main sequence source stars, 10 times smaller in radius, are very easily able to detect Earth mass planets. And at wider separations, you can see Earth mass planets with giant stars. So this now shows comparison of simulated planets, and so these are the data here are what you get for an Earth mass planet, and if you change the mass by a factor of 2, you get this green curve or this blue curve, and then the cyan one in the background is with no planet. So it's basically measuring that shape of the light curve that tells us the mass, and we get the separation by the magnification of the star at the time that the planetary signal occurs. That's in units of the Einstein radius, however, it's not in physical units. Okay, so so this now is showing, this is for the second planet found by microlensing. This is showing the magnification at different locations with a star here and a planet here. Okay, so there's 2 of these caustic features. One is associated with the planet. The other is associated with the host star, and so but we don't measure these magnification patterns. We need a source behind it. And so that source could pass like this. So it could pass along here, and this, covers the part of the magnification pattern that is the same as a magnification just by the star. So we wouldn't be able to detect the planet in that case. This one, however, crosses planetary caustic, and then we would see these bright features in the light curve. And then this one passes the central caustic. Now, the central caustic is smaller, but also you can tell when you're getting close to it because the magnification due to the star is increasing and getting very large. And so one of the ways that we found planets in the early days of using this is that we would announce that we have a high magnification event coming up, and we get a lot of observers to observe it. And in fact, because of the high magnification, even amateur observers could contribute. They would have small telescopes if they really needed the high magnification to help them out. But also, they had one big advantage over professional astronomers, is that no one else is allocated to use their telescope, so they could use it when they wanted. Typically, it just meant that they'd observe all night and then go to work the next day, which was not so easy, maybe, but a lot of amateurs really helped out with that. So this is now the current sort of the current state with planets that we found from the ground. I think I showed this before, and now we're going to show some statistical results from this. And so the statistical results are primarily from the MOA collaboration, was the first high cadence survey that had a big enough field of view to observe many tens of square degrees per hour, and detect the planetary signals in the survey data. This figure, so the Japanese map of New Zealand, indicates the original is originally a project of Japan and New Zealand until I joined shortly after they started. And so this is results that were published in 2016. And so on the right here, these are the number of planets discovered in mass ratio bins. And so mass ratio is something we can get directly out of the light curve. Getting the masses is a little more complicated. I'll talk about that in a minute. This is our survey sensitivity. And so these contours here with, 3 or 5 or 20, if every star had a planet at one of these locations, and these contours say how many we would detect. For some of these high magnification events, we actually have almost identical light curves at different separations, and so that's why these things are connected with lines and open circles. But we get the mass ratio pretty accurately. Okay, and so the survey sensitivity function then tells us how many planets we could detect. So we have the number of planets we have detected, and then the survey sensitivity tells us how many we could detect if every star had such a planet. And so that gives us a correction for the total number of planets. And so then we get this red histogram is this corrected survey, and then we have a broken power law model, which is given here, but then the shaded region is the error bar on that broken power law model. So we're measuring a lot of planets down to mass ratio of 10 to the minus 4, and then our sensitivity drops off and the number drops off as well. We're not sure in this analysis whether that drop off is real or just because of the lack of a sensitivity. But anyway, so now we're going to compare this to some what are called population synthesis models predicting for the core accretion theory. So the core accretion is a sort of standard theory where you build up a planet first by solid matter collecting, first by chemical reactions, and then soon by gravity. And then when it gets massive enough, it starts accreting gas. But to do those calculations, it's very complicated, and so they have a bunch of approximations they use to do the calculations. And so if those predictions are not correct, it could be that it's a problem with some of the approximations and so forth. So they basically have to follow the discoveries. And so this is now we did a paper with two of these population synthesis groups. So this is the same graph I showed before with the results corrected for these detection efficiencies. And so with the standard models they were using with planetary migration that they put in to explain all these hot Jupiters that were being found, they under predicting the planets over most of the range where we're observing. So they tried turning off planetary migration. And you see that at high masses, then they're slightly over predicting. But there's a factor of 10 discrepancy between mass ratios of 10 to the minus 4 and 3 or 4 times 4 times 10 to the minus 4. And that roughly corresponds to masses between Neptune and Saturn, or sort of 20 to 80 Earth masses. So that was the gap what was being predicted due to this runaway gas accretion process. And so we don't observe this sub-Saturn mass gap. And so that suggests that this runaway accretion scenario is not quite as important as thought. Okay, there's another microlensing group that started up later, but they had advantage of having 3 telescopes in different longitudes, one in Chile, one in Australia, and one in South Africa. So when they're lucky and the weather's good everywhere, they can get pretty much continuous coverage, which is useful because a lot of these planetary signals last for a few hours or a day, and continuous coverage is sort of needed to get a continuous data set. So so this is their results. They have their system has higher sensitivity. so they used data from 4 years, but a mass ratio is higher than 10 to the minus 4. They only used 2 years of the data, and so they get something that looks a little bit similar, but there is this slight dip in the mass ratio function, but not at the value where it was predicted by those population synthesis model at one higher bin. And part of this difference, at least, is due to, it looks like it's due to basically random noise, that there are a lot of events observed in this mass bin before this KMT telescope started observing, and then the first 3 years they're observing, there were many fewer. Probably that's just a statistical fluctuation, but when you combine them, you see that you get something that's pretty well fit by a power law, and this cutoff at low masses is not as strong as in the MOA sample. Okay, so this suggests then that they'll be collecting more data, so it's possible that the KMT group is actually seeing a real signal that there is a little dip in the mass ratio function at sort of mass ratios between Saturn and Jupiter, but that dip is not as large. It was predicted by these other theories. So and then Roman is going to really help with this, so just to talk a little bit about what this means. So this is a drawing that's supposed to show what the snow line is, and so basically this is supposed to be a cartoon of the protoplanetary disk, and it's getting heated by the star, so the inner parts are hot, outer parts are cold, and beyond this frost line or snow line, which is thought to be about 2.7 astronomical units in our solar system, then this is where you can get ices that form and have more solid material to form the cores of planets like Jupiter and Saturn. And so what's the original calculation showing for runaway gas accretion is basically using a spherical approximation, which works well if the viscosity in these disks is pretty high. And so basically what's thought to happen is that you grow a solid core in, start growing in chemical and then gravitational processes. And then after, in this case, 2.5 million years, you get sort of an equal mass of gas and solid material. And then you get this runaway growth phase where the mass grows very quickly. And so it's thought that because this goes very quickly, then there wouldn't be many objects ending up at these masses because it's unlikely. And the thing that stops it is there'll be radiation from the star or actually from nearby stars that can blow off all the gas. And once the gas is gone, then you don't get any gas accretion. And also, that it's thought that the water on the Earth is originated from sort of outside the orbit of the Earth. And they can actually determine this from the deuterium to hydrogen ratio, that the ice that forms, where the ice forms depends on the deuterium to hydrogen ratio of the ice. All right, so, but if the viscosity is low, then you can get more complicated situations. And this is a simulation of one, showing there's a protoplanetary disk, but inside that there's a circumplanet disk. And it's difficult then for the gas that's falling in to lose its angular momentum. And so the gas that falls in is mostly falling in on the poles, and actually the gas in the disk tends to move outward, and this slows things down a bit. And so here's just a picture of without this snow, the lines of accretion. It shows sort of where that circumplanetary disk is forming. And so it's possible that this mechanism is preventing these runaway gas accretion from being a real dominant process, although it still may occur. All right. And yeah, so here's just a comparison to some radial velocity data that also shows no sort of gap. This is data from a Swiss group, the one that found actually the first exoplanet. And so these are curves. These are curves in different period bins with all the planets found, and I tried to model this with a gap. And so some of them have best models that have a little bit of a gap, but these dashed these gray areas, the dark gray and the light gray, are the 1 and 2 sigma extents of all the models that fit the data. So there's no significant detection of any kind of gap at a different separation. All right. And so mostly we've been talking about this mass ratio function, but of course planet properties may depend on the host star mass. And in fact, the data from Kepler suggests that there's a pretty strong dependence. And so, and this actually was a major selling point of the space-based microlensing survey that's now part of the Roman mission, is that we can get masses of most of the host stars. Okay, so we do this using 3 different mass-distance relations. So 2 of them are directly from sort of microlensing data. And so one is the angular Einstein radius, and you can get this from events with finite source effects because you can determine the angular size of the source star from its brightness and color. You can also get it if you can observe the lens and source stars separating after the event, which is what we do with events we know about. But Roman will actually find some cases of planetary cases where we see the 2 stars approaching, and then in the final season of observations you see the microlensing event. So either of those can give you the angular Einstein radius. There's the other one is called the microlensing parallax, and this is kind of the opposite. So the angular Einstein radius is sort of the projection from the Earth. Here's a lens, and then when you take the Einstein radius projected to this distance of the source, that's the angular Einstein radius. But you can also project in the other direction to the distance of the Earth. Okay, and so you need some measurement of microlensing measurement of something to do with the position of the observer. And so one way is if you can see the effect of the orbital motion of the Earth in the light curve, that relates this projected Einstein radius to the light curve you see. Also, if you observe from 2 telescopes that are separated by far, we have 1 or 2 cases where we can actually see this effect from observations at 2 different observatories on the Earth. But mostly, you can't measure it that way. And then, the third method then is just the brightness of the star. That you see the lens star, you measure its magnitude, and then you have a mass distance relation of stars that are consistent with that, because we know how the luminosity of stars varies with their mass. Okay, so here's just an example of a mass distance relation from from measurement of the brightness of the star. Now, to do these, to measure both the separation of the source and the lens, and also this brightness of the lens star, it's difficult to do it from the ground. Here's the image of a microlensing event, position of a microlensing event observed from the ground and from space. And basically, a lot of these things that look like individual stars in this ground-based image are actually multiple stars. So you have to be able to separate, the source star from the lens star and maybe some unrelated neighbor stars. And so actually, we need very high angular resolution observations to make use of this to make use of this, well, both to measure the lens source separation changing and also to measure the brightness of the lens star. Because otherwise, if you're trying to use ground-based data, there can be multiple lens. There are very likely to be multiple stars that are contributing, and you have to separate out the one that's actually the lens. So this is an example of a mass measurement that's just come from parallax and finite source effects. So, so here's a light curve. This case, the lensing actually destroys one of the images and decreases the brightness here. And then, but then it crosses over a caustic and has these brighter features. And so this, we can measure how long the source radius crossing time is. And we measure the microlensing parallax, but this is a two-dimensional vector, and we're determining it with the acceleration of the Earth effect. And that acceleration of the Earth, looking toward the galactic bulge, which is almost in the ecliptic plane, is almost all in the east-west direction. So we get a much better measurement in the east-west direction than we get in the north-south direction. And so this one we can determine the mass of. Okay, so the typo here. This is microlensing parallax, not parallax. So there's one telescope, well, actually two telescopes now that are, well, three actually. But the first telescope to go in the same L2 orbit that Roman is going on. So L2 is a Earth-Sun Lagrange point where that moves at the same period as, orbits the sun at the same period as Earth does, even though it's 1% further away. And the reason it has the same period, even though the orbit is further out, is because it's feeling both the gravity of the sun and of the Earth. There's also the L1 point that's at 99% of the distance from the Earth to the sun, and that's where they put telescopes to look at the sun. And that, is also feeling the gravity of the Earth and the sun, but the Earth is pulling on it, pulling it away from the sun instead of pulling it toward the sun. And here is a case of a binary lensing event that was observed by this Gaia mission, which is a European mission that's also at L2. And you see that these two curves show the light curves observed from the ground and light curves observed from L2. So there's a difference in these caustic crossings of about 4 hours. And so that means you can use that 4-hour difference to tell you what the microlensing parallax is. That's not a good, if you have a single lens event that lasts a month, a 4-hour difference is pretty hard to see. But planetary events tend to have very sharp features, either just because the planetary feature is very short, and also they sometimes have these caustic crossings that give very bright signals. So we're expecting to get microlensing parallax measurements from simultaneous observation from Earth and from L2. Also, there's another wide field telescope at L2, the Euclid mission that was recently launched by the European Space Agency, and we're hoping to get simultaneous observations with Euclid and Roman after Roman launches. Okay, so much of the work that we've done trying to develop this method for measuring masses using higher angular resolution imaging uses a laser guide star system on one of the Keck telescopes. This is a case where both the telescopes are observing in the same location, the galactic center, and they're using this laser guide star method to correct for atmospheric distortions and get much higher angular resolution. So here's several results showing the lens and sources for a number of events that occurred in the past. So here's, we identified the lens and the source. Sometimes they're not really fully separated, but also they have this elongated image and you can fit to where they are. And then down here, the blue curves show the masses that were consistent with the model without the follow-up data. And then with the follow-up data, you get a precise measurement of the mass in the red. So we developed this method. Sometimes there are complications. Well, for this event, you note that the lens is here, but there's another bright spot here that is not the lens. And this actually is due to imperfections in this correction. Sometimes the Keck telescope has multiple mirror segments. Sometimes one of those is a little bit out of alignment. So we have to model the point spread function with lots of other stars, and those other stars indicate that this is a feature that occurs for all the stars, whereas this one only for this star. But sometimes we don't have any detection. In this case, we had strong constraints from this microlensing parallax that the event, the mass could not be less than the lowest mass star, and it also couldn't be as massive as a neutron star or a black hole, but we still don't see it. And so the only solution then is it's a white dwarf lens. And so this is actually the first case of sort of an analog to what the solar system is going to happen after the sun dies and becomes a white dwarf. It'll lose some mass, and Jupiter will likely drift outward and be similar to the lens for this star. So we have JWST observations that are hopefully going to detect the white dwarf host. And then here's an example of one where we had two models that could explain the data, but they explained it with different velocities between the lens system and the source system. And the stellar binary model matched the follow-up observations, and the planetary model did not. All right. And then so the direction of relative proper motion is parallel to this microlensing parallax vector. And so for one of these events, we had a microlensing parallax that's measured here, but when you had the measurement of this relative proper motion, we can get a precise measurement, and that gives us a more precise mass. All right, so here's cases of what these mass-distance relations look like. So here, this is due to the a Keck measurement, and then this angular Einstein radius was measured. This is the one I just showed where there was a very weak constraint on parallax, but from the measure of the direction of relative separation, we could reduce it to this green curve, and then we all observations in multiple pass bands, they all cross at the same point, giving us a mass. And this one is similar. It has microlensing parallax, 3 color measurements, all converging at the same point. All right, and here's a few others. This one is one where there was a mistake in it was some systematic error that wasn't noticed in some of the ground-based data, and when that got corrected, then we got a value that matches both this theta E measurement and the measurements in these different pass bands. There's one complicated event which has not only a star and a planetary lens system. It also sees an effect of the orbital motion of the planet, but also the orbital motion of the source, because the source has a companion. And so the orbital motion of the source and the planetary orbital motion actually can give a signal similar to the microlensing parallax. So we actually have two solutions. So one with a large parallax, which gives a low mass of around about 0.25 solar masses. The other one gives a high mass of around 0.7. And the reason for this is partly because we only have this measurement of the brightness in one infrared passband. If we had it in shorter wavelengths, then we could resolve them. And so we're proposing to get some more observations of that. So anyway, this tells us that really these mass measurements tell us that these sub-Saturn mass planets are common, and it's not just a feature in the mass ratio function, but also a feature in the planetary mass function. All right. And so Roman is going to be able to do the same thing, and it's going to have a lot more images, although we won't, the separation time in images will be a little bit smaller, but there's a lot more images, so we expect to be able to do the same thing and do better, because Roman will have fainter source stars. All right. So now finally I want to talk about the free-floating planets, which is sort of the latest result from microlensing. So, and to some extent, the free-floating planets are shown here. These are planets that are detected without any microlensing signal of a host star. Okay, and so there's 3 microlensing groups that have found these. There's Ogle collaboration, which was the group that found the first microlensing event toward the galactic bulge a couple weeks after Macho found the first microlensing event toward the Large Magiellonic Net Cloud. And then the KMT-net survey that I showed some results from before. But the MOAA survey is the only one that's done the statistical analysis. And so basically, here's a distribution. These are Einstein radius crossing times. And so this is Einstein radius crossing times proportional to the square root of the mass. And so there's a bunch of events down at very short times. Time scale is less than a day. And so here's the events that have time scales less than half a day. And a couple of these have finite source measurements. So we can not just measure the time scale, we can measure the angular Einstein radius. And one of these with angular Einstein radius of less than a microarcsecond has a mass that's most likely less than Earth mass. Yeah, so, and then the one thing that actually, the measurement of this angular Einstein radius is actually something that seems to distinguish pretty well between planets and stars or brown dwarfs. And so here's a cumulative distribution of single lens events that have measured angular Einstein radii from several different groups. And so there's a gap between 10 microarcseconds and 25 microarcseconds where there's no detections there. And so the ones with less than 10 microarcseconds we think are due to planets. And there's 2 of them that have predicted masses that are probably a little bit less than Earth mass. One found by the Ogle collaboration here, and this one found by the MOAA collaboration that's in the statistical sample. All right, and so to do this analysis, we need a detection efficiency. It depends on both the source radius and the angular Einstein time, and this is sort of the distribution. Some of them have limits on the angular size rather than, but we use all this data for analysis, and then the detection efficiency depends on both of these. And so here's some plots of what the detection efficiency looks like in different sets of units. Anyway, so we find if we fit a power law mass function, that's shown here in green. So that extends it with a power of mass to the -1 or so, or maybe it's minus 0.95 or something. And then, and if we use a model that doesn't extend below lowest mass measurement, it follows this pink curve with the uncertainty. So the most surprising thing is basically here that these models indicate the number of free-floating planets is about 6 times larger than the number of known bound planets. The total mass is not larger. But it also, and these are, because of the small number of events found, these are pretty large statistical errors. So it could be only a factor of 2, or it could be a factor of 10 or 11. But this also suggests that Roman should find about 1,000 free-floating planets down to the mass of Mars, including around 600 between the masses of Mars and Earth. All right, so yeah, so some of the theorists have looked a little bit about the formation of free-floating planets, and it's generally thought that these mostly come from, at least the low-massed ones, mostly come from gravitational scattering of the planets. But the scattering is a lot more effective in circumbinary systems. So like here, or where the planet's orbiting 2 stars. And so Coleman and DiRocco have done a prediction of what the mass function should look like. And they get this thing with a big peak around 8 Earth masses. And this is supposed to be the pebble, what they call the pebble isolation mass. And so this is the pebbles refer to a variant of the core accretion model called the pebble accretion model. And so, but what's thought to happen is that binary star systems like stellar systems have protoplanetary disks, and so the thought is that when these planets get up to this pebble isolation mass, they become massive enough so that they can undergo this migration due to gravitational interaction with the disk. And in most circumstances, this causes them to move inwards. Okay, but when they move inwards to a circumbinary planet, they're going to reach a cavity in the disk where orbits become unstable due to the binary stars, right? So if you had a single star, then that disk would go in much closer to that star. But with binary star, when orbits become unstable, then the gas and dust that was in orbit would also spiral in or spiral out. And so what happens is once they reach this cavity, there's no inner disk to pull on the planets to pull them in further, and so they collect there. But when they collect there, that increases their density. They're more likely to scatter each other. And if they start scattering each other, then eventually they'll get ejected, and most likely they get ejected when they get scattered close to one of the stars. And so, so it's thought that even though, circumbinary planets, circumbinary systems are much less, several times less common than planets around single stars, they dominate these ejections. Planets ejected, planet ejections also have smaller velocities and are more likely to maybe put planets in very wide orbits where they're actually hard to detect by microlensing, but with the follow-up observations, if there's a host star there that moves at the same speed that the lens should be separating, then that would be an indication that they actually aren't free-floating but are in just very wide orbits. And so that might distinguish between ones that are, have an interaction with a planet or with a star. But also, this provides a window on a phase of planet formation that we couldn't really get a handle on for single stars, because these stars at the pebble isolation mass, they're at a stage of the formation when the formation would continue if they weren't ejected. And so if we see this feature, that might be an indication that this pebble accretion model really works, and there is such a thing as a pebble isolation mass. And so here's a calculation led by one of the postdocs in my group, William DiRocco. And this shows this green curve is the prediction from the MOA analysis that I showed before with uncertainties. And so they're pretty large error bars. And then the blue and orange dashed lines are the value predicted by this single power law model, and then predicted by this model, including the pebble accretion. And then these error bars are the measurement errors expected from Roman. And this is not actually using any parallax information that we might get from ground-based observations simultaneous with Roman or with simultaneous Euclid and Roman observations. So it looked like these free-floating planets may be able to, give us some more clues on a part of planet formation that we wouldn't otherwise have any clues for. All right. Okay, so so we're really looking forward to the Nancy Grace Roman Space Telescope. I personally have been sort of working on concepts like this since 2000. Actually, The concept actually came from conversations with another one of your speakers, John Mather. And it's on schedule for an October 2026 launch, since the government didn't shut down, in which case it would be delayed by a week, I guess, by now. And it's on schedule, under budget, and the schedule reserve lasts until May 2027. So if we launch before then, we won't have to ask NASA for any more money. All right. Are you ready to entertain questions?
How you doing? My name is Paulos. I am not a member. Simple question regarding your notation. You had lots of portraits up there of various different scientists, and you had a number and a plus sign after their number. What is that indicative of?
So, so the name is the first author of a paper. Plus means there's more than one author. And the number is the last 2 digits of the year that is published.
We're going to use the red microphone again. We're going to.
Hi, Matt Kaywood, member. Do we have the tools or the mechanisms to see non-planetary features of these extrasolar systems? For example, asteroid belts or other more exotic things that that we might not have good models for?
We haven't had that ability with the ground-based observations. There's some discussion about whether that'll be possible with Roman.
Is there a way? I mean, if we were to be able to detect enough planet in a particular system, could we make inferences the same way that we do about sort of these laws of solar system evolution?
So we do know a lot about multiplanetary systems in short period orbits from Kepler. Multiplanet systems are a little harder to detect with microlensing. And it's in part because if that plot where I showed the different trajectories across the magnification pattern, some of those trajectories are missing the planetary signals. And if the mass of the planets are low, then those signals to the low mass planets cover smaller areas, so those are harder to detect. So in one of my early calculations, I looked at the possibility of detecting Earth and Jupiter systems. And so it's pretty unlikely to detect an Earth in an event where you have a Jupiter detection. But if you have an Earth detection, then detecting a Jupiter was close to 50%. So, yeah, so it's, so I mean, we can make some inferences about that. And with Kepler, if all the planets are transiting, that can depend on the mutual inclination. And so for some systems, you have so many planets detected transiting that there can't be other planets like in between, because that would make the system unstable. But when there's more scatter in the orbital planes of the different planets, then you can't really count them all from transits. So we can do statistical analysis, including the possibility of detecting the multiple planetary systems, but it's a lot easier for more massive planets than for low mass ones.
Blue microphone back there.
My name is Timothy Thomas. I'm a member of the society. I'm wondering about what was called Boyle's Law, I think, where the planets around our sun are distributed in a logarithmic based in fashion if you ignore their size, and some are asteroids. I'm wondering if similar type distributions exist or have been found on other stars.
So I think I've seen some papers that argue that orbital stability gives you something that you could derive a similar law to Boyle's law for a lot of planetary systems. I don't think that people are I mean, I don't think that. I think the thought is that Boyle's law is like partly an accident, but the stability requirements and maybe some formation mechanisms are such that they make such an accident pretty likely. So there may be other things like Boyle's law, but they'd be like a little different for each system. And then sometimes there's controversies about how many planets, like in radial velocities, how many planets are around in the system, and one group will model with a bunch of planets in circular orbits, and someone else will say, oh no, there's one fewer planet, but one of them has an elliptical orbit. And so, you can't really. Well, that one event I remember is one system. Then someone else wrote, oh no, all the ones you're arguing about, none of those are planets. Those are, features in stellar activity.
So your answer is no. There's no evidence really that such a pattern exists around other stars yet.
Well, I think there's evidence that suggests that patterns like that, similar to that, are common, but not any particular version. But it's not like there's been a lot of literature on that. I remember seeing one paper, I think.
We're going to go to the red microphone, then we're going to take some questions from the chat on the YouTube. So red microphone, name.
Mike Moore, I am a member. Early on in your discussion, you mentioned that the potential solution to dark matter was were all these free-floating, invisible things. With the data you have, do you have any feel for whether that actually is a potential?
Yeah, we're not working on it anymore because that's been rolled out a long time ago. And recently, there have been people trying to push black hole dark matter. So when LIGO was detecting these black hole binaries, some of the masses were a little higher than people expected, and we're wondering if those could be dark matter. But that's pretty strongly excluded. And then there's maybe a push to look at much lower mass primordial black holes, but so far there's no evidence for that. And the original Macho project was focused on type of objects that we knew about, not black holes of an asteroid mass or something. And so there's still some work on the sort of black hole angle, but most of the parameter range is ruled out, and certainly the ones that are made of ordinary, the sort of objects that we know exist in the universe, those are all ruled out.
Take a few questions from the chat on the YouTube live stream.
Our first question comes from Joel in Maryland, who is a member. Can you detect exoplanets by observing gravitational waves? And can you use microlensing with gravitational waves as opposed to light to detect them?
I would say no.
Not energetic enough.
Yeah, well, yeah, I don't. The gravitational fields of planets are pretty small, and I'm not sure that we have detectors that can detect the wavelengths that might be influenced by planets. I think we don't, and also, I mean the probability of seeing any given time seeing a planetary signal for microlensing for a given star is is less than 1 in a billion. And there's not many gravitational wave detections compared to a billion. So Yeah. So I think that's pretty far away. Yeah.
Yep, we have a second question from Dave Rabinovitz, who is from Oregon, who is a member. Has anyone simulated what a faraway observer could detect in our solar system using these methods?
Well, I mean, certainly simulated what we could detect from a system like our own. I mean, we're at a different position in the galaxy, and it would depend on where they're located, actually. So if they're located interior to, closer to the galactic center than we are, then when they look towards us, they're looking at a much sparser sample of source stars. So the probability would be a lot lower. If they're further out, then the probability could be higher. And it sort of just depends on what their distance is. But yeah, I mean, certainly other observers could probably detect us. On the other hand, since the odds of seeing microlensing by a star are only around a few in a million, the odds that they see any microlensing by our star are pretty low. So so if there's a million such observers, then one of them could probably, or a couple of them could probably see the microlensing of the sun, and then you need another, at least another 1,000 probably a factor of 1,000, so a billion, and then you kind of run low on the stars in the galaxy. If you want stars further out, if we have a billion of them, well, they could just wait millions of years.
Like,
Maybe the question was under optimum conditions. But let's go to the blue microphone.
Hi, my name's Lynn Fellman. I'm a member. Thank you for the good talk.
You're
So could you just remind me how many exoplanets you've identified so far? And are you predicting how many you might find once you start looking again in the next year or two? And when would you start getting data back once you get out there?
So when you say planets I've found, do you mean papers that I'm on? Do you mean the number of microlensing planets found, the total number of exoplanets found?
Yes, the total number so far.
From microlensing or from everything?
Take your pick.
So microlensing, it's a few hundred. Total is, I don't know, 7,000 or 8,000, I think. Actually, the biggest number that's going to be found by our telescope, I didn't talk about at all, which is transiting planets in the galactic bulge. And these are not going to contribute that much to the statistical analysis because they're the same type of planets and actually the ones that are easiest to detect by Kepler. But we'll see lots of those, and we'll learn a bit about how those properties might change for those planets in the galactic bulge compared to in the galactic disk. So we're supposed to launch in late October 2026. If that happens, the first observations for our program will start in late February or early March 2027, and we should have some discoveries out a couple months later, so mid 2027. If we get delayed all the way up to our end of our schedule reserve, then our first observations would be in the fall of 2027, and so then a 6-month delay in the first results. Some of the mass measurements, though, are going to require 4 or 5 years of data, if we want to be able to see the lens and source stars separating. But there's another effect that we can also measure for at least some of the events, which is, I didn't talk about, but it's microlensing. Is that when the star gets brighter, it's getting brighter by these different images, But oftentimes one of those images is a lot brighter than the other, or there are several that are brighter. And so when we're seeing the combined light from all those images, it moves a little bit. And so that actually is going to help us to make some of these mass measurements and ones we can get out in the first year. So.
Red microphone.
Good evening. This is Michela Muñoz, a member in progress. First of all, excellent talk and congratulations on all your discoveries. So my question, I was wondering if the data you gather from Roman plus maybe coordinated or combined with ground observations, if that will help to have a better understanding of the Einstein gap that is thought to separate the stars and brown dwarfs from planets. Thank you.
So the observations from multiple telescopes, either from Roman and Euclid or from Roman and the ground, that actually isn't going to tell us about the Einstein gap, because Einstein gap comes from the angular Einstein radius, and that will come from finite source effects, where we see, and finite source effects for low mass planets are almost always present, because if the angular Einstein radius of the lens is no larger than the source size, then you can't see something that looks like a point source microlensing event. So if we just have the angular Einstein radius, then there's a bit of a degeneracy in the interpretation. You get the same angular Einstein radius from a lower mass planet in the disk or a higher mass planet in the bulge. And so the observations from the other telescope are going to break that degeneracy and give us also directly the mass. I don't know if I showed some equations that giving you the mass distance relations. But the distance relation, the distance part of the distance relations for the microlensing parallax and the angular Einstein radius are the inverse of each other. So if you multiply those two equations together, you get an equation for the mass as a function of the angular Einstein radius and this microlensing parallax parameter. So we'll be getting direct masses from the simultaneous observations. And the angular Einstein radius will come from events with finite source effects. And so most of the very low mass planets will give rise to those.
I think this is the last question, red microphone.
I'm Bob Hershey. I'm a member. What kind of improvements are expected with the Roman compared to what you had?
Well, so we're sensitive to much lower mass planets, and also particularly ones at shorter separations. So from the ground, the low mass planets are really hard to detect if they're located inside the Einstein radius. So Roman is needed to get some handle on sort of planets like Earth mass planets in the outer part of the habitable zone, which Kepler wasn't really sensitive to. And then, for these free floating planets, we'll have probably 100 times more. And we'll so we can do a lot better statistics, and also we're expecting to also study population of isolated black holes or stellar mass black holes.
We have a question, blue microphone. Sorry. Lloyd?
Hi, Lloyd Mitchell. I'm a member. I have two questions. One is, are there other mechanisms for ejecting and making free floating planets like supernovas or being thrown out by another planet? And then the second is, does NASA see any risk of free floating planets for us?
So supernova would definitely produce some free floating planets. Stars that go supernova are pretty rare among stars, and the stars that turn into white dwarfs, they go up to about 8 solar masses. And I think, there's evidence for planets that far around stars of a few solar masses, but planet scattering definitely can produce some, but the circumbinaries are thought to be more dominant. Also, very widely separated binaries also produce more than individual stars. And basically, what happens in very wide separations, the orbits become sort of unstable to perturbations by passing stars. And so if you have, a separation of hundreds of AU or 1,000 AU, a passing star might perturb that to a very high eccentricity. So it falls in, and it can, scatter and can remove some of the planets, either its own or the sorry. The binary system would be on a very high eccentricity. So that they can trade planets or eject planets. About what NASA is concerned about. I had more questions about this topic from TV networks. The Discovery Channel asked me after I published a paper on finding black holes by microlensing. They wanted to know what are the odds that a black hole would, a rogue black hole would collide with the Earth. And I said, that's not really the danger from a rogue black hole. I mean, the thing about black holes is that they're really tiny, not that they're especially massive. And so, a rogue star is more likely. But I said, more danger from a rogue black hole would just be that it perturbs orbits and puts us in an uninhabitable orbit. And so Discovery Channel was not interested in that. It wasn't dramatic enough. But then several years later, we published a paper on rogue planets, and another network called. It was the Weather Channel. And they really liked the idea of the rogue planet coming in and perturbing Jupiter and then perturbing the Earth.
So, all right, thank you very much. Before you go, we have a few gifts for you, which will be in the back of the room, but so everybody knows what they are. We have a framed copy of the announcement of your talk, signed by all members of the General Committee on behalf of the membership as a whole. We have a copy of volume 17 of the PSW Science Bulletin, originally published as the Bulletin of Philosophical Society of Washington. Volume 17 incorporates a lot of the original material from Volume 1 regarding the formation and purposes and intended conduct of the Society and its members, and a number of histories and a list of all our Joseph Henry speakers. We have the annual Joseph Henry Lecture, and also the Nobel Prize winners who have been speakers, and some minutes of previous meetings pairing an early meeting with a later meeting on the same topic, such as the report on malaria as, the mosquito as the vector of malaria, with a much more recent talk on genetically engineering the mosquito so they can't take up the parasite and can't transmit the disease. And it's just intended to show that many topics that were of interest to scientists when the Society was founded continue to be of interest today. And finally, we have a PSW ribbon emblazoned on the side with the 3 bars representing the symbol for inductance, which is named the Henry for Joseph Henry, our founder. And we hope you'll enjoy wearing it. And we hope, since you're not too far, you'll come up from time to time and enjoy PSW lectures. And with that, let me thank you very much. And I'd like to tell you about our upcoming meetings. Our next meeting is 2513th on April 4th. The speaker will be Joshua Semeter, professor of electrical and computer engineering at Boston University. He'll be speaking about unidentified anomalous phenomena, which are previously known as unidentified flying objects. He will be talking mainly about what he found on when he served on the NASA panel that was instituted a few years ago and gave a report that probably satisfied nobody. But there was some interesting stuff, and he'll be talking about that and about what their conclusions were. That should be an interesting talk and a bit of fun, I think. I will not talk about all these other lectures except to highlight one, which will be the 2518th meeting, which will be the last regular open lecture of the Spring's lecture series. On June 27th, the speaker will be Jason Dworkin, who is the senior scientist for astrobiology and project scientist for OSIRIS-REx. He will be speaking on analyzing the samples that the OSIRIS-REx mission brought back from the asteroid Bennu, which had some very interesting results. It was a colossally great success, and I look forward to hearing from him. And with that, let's give a little thank you for our volunteers. And one last item, don't forget to return your badges. And with that, I'll accept a motion to adjourn the 2512th meeting. A second. All in favor? Any opposition? Hearing none, the meeting is unanimously adjourned to the social hour and the refreshments at the back of the room.